Okay, so today we have Riccardo Comi, who will tell us about mirror dualities with 4 supercharges. Take it away.
Okay, thank you, Julius. So first of all, for giving me this opportunity of giving this talk. And as he said, it will be about mirror dualities in theories with 4 supercharges, and is based on an ongoing work that I'm doing together with Sergio Benvenuti and Sara Pasquetti. So the plan is to start with some introduction. I want to review the most important aspects of mirror duality in theories with 8 supercharges. And then I will just stop for a moment to introduce a theory called FMUN, which I will then use it as a building block for mirror dualities in 3D n equal to 2 theories. So that then I can give you an example of the mirror dual of the n equal to 2 UN adjoint SQCD. And we'll discuss the most important features of this proposal and also how you can derive this type of dualities using this strategy of the dualization algorithm. And then also in the end, I want to discuss a bit about our interpretation of this whole story from the point of view of brane system preserving 4 supercharges. So as I said, let me review some important facts about mirror duality in 3D n equal to 4 theories. That, as you very well know, it is a relation between 2 theories that acts by swapping the Higgs and Coulomb branches. And a major breakthrough in this topic happened when it was understood that mirror duality is induced from S-duality acting on the brane setup, from which one can engineer 3D n equal to 4 theories. But later it was also shown that abelian mirror duality can be proven at the QFT level just by dualizing a theory piecewise and assuming a basic abelian mirror duality, which is U1 with a single flavor being dual to an hypermultiplet. And very recently, this strategy has been extended to a more generic case of non-abelian theories, when it was introduced this so-called dualization algorithm that again allows to dualize a theory piecewise and assumes a set of non-abelian mirror-like dualities. And all these dualities assumed can be proven starting from more fundamental cyber-like dualities. And I also want to mention that this strategy has been extended recently to the whole SL2Z group. So not only to S dualities, but also to any other element of SL2Z. So that's the short story for theories with 8 supercharges. Now, what about theories with 4 supercharges? So there are mainly 3 questions that I will try to answer throughout this talk. First of all, I want to understand if we can find exact mirror duals for 3D n equal to 2 theories, which is a task that has been accomplished for the abelian case, but it's not clear in the non-abelian one. And there are just some proposals, but a full, complete solution is not known yet. And I also want to understand if these 3D n equal to 2 mirror dualities are consequence of more fundamental, like cyber-like dualities, which again is true in the abelian case, but not very well understood in the non-abelian one. And then I also want to see if this quantum field theoretical approach can teach us something about brane setups preserving 4 supercharges. So, as I say, let me review, I hope very fast, an example of a 3D n equal to 4 mirror duality, which is the case of the UN SQCD, just to set the stage. So let me say that in this talk, I will depict all the theories in an n equal to 2 language. So for example, for the SQCD, we have a UN gauge group, so together with some n equal to 2 vector multiplet. And then we have this extra chiral, which is in the adjoint representation, and the F flavor hypermultiplets split into pairs of fundamental and anti-fundamental chirals, Q and Q tilde. And also, it's very important to notice that n equal to 4 supersymmetry is forcing this cubic interaction between A, Q, and Q tilde, so that before we had a UF times UF flavor symmetry rotating independently fundamentals and anti-fundamentals, but now this is broken down to the diagonal UF subgroup. And it is known that this theory is mirror dual to this theory on the right, which is given by F-1 unitary gauge nodes with this pattern of 2 ramps of increasing ranks from 1 to n, and this plateau with flavors on the side. And again, let me stress one more time that supersymmetry is forcing a cubic interaction between bifundamentals, flavors, and adjoints. So now what I think, well, arguably, what I think is the most important feature of mirror duality is that it acts by swapping topological with flavor symmetries. So in this example, in the SQCD, we have a SUF flavor symmetry rotating the flavors. And for generic NNF, we have a U1 topological symmetry. And these are swapped, meaning that we map the U1 topological symmetry into the U1 flavor symmetry of the mirror theory, and the SUF flavor symmetry into an emergent SUF topological symmetry coming from the enhancement of all the U1 topological symmetries of the UV theory. And this pattern of enhancement becomes clearer if one looks at the operator map. So here in this slide, I'm also writing the way we parameterize the theory in red. So for example, in this first picture, X is the set of fugacities for the SUF symmetry, while on the right, these parameters inside round brackets are the Fi parameters associated to the topological symmetries of the given unitary node. So as I was saying, we want to map operators, and in the SQCD, we mainly have two types of operators. We have the mesons and the monopoles. The meson is in the adjoint representation of the SUF flavor symmetry, so we can think of it as some F by F traceless matrix, and we can map it into a collection of singlets and monopoles. The F-1 diagonal components are mapped to the traces of the adjoint fields in the mirror, while the off-diagonal components are mapped to monopoles that are constructed by taking a positive or negative topological charge under a string of consequent topological symmetries. And a similar story happens for the two monopoles of the SQCD. So we map them to the two mesons that we can construct in the theory. So we take the flavor multiplied by this string of bifundamentals and then the other flavor. There are two such operators that are oppositely charged under the U1 flavor symmetry, and we map them to the two oppositely charged monopoles. Okay, so
I have a question.
Yeah, sure.
You're using here a notation of bidirectional arrows.
Yes.
So the supersymmetry is 8 or 4 supercharges?
So the language is n equal to 2, so 4 supercharges, but the theory is actually n equal to 4, 8 supercharges. We can recollect these fields as n equal to 4 representations.
I see. Okay, thank you.
Okay, so I was saying in the beginning that it was a major breakthrough when it was understood that mirror duality is induced from S-duality acting on the brane setup. So here the story is that we can engineer 3D n equal to 4 theories using NS5, D5, and D3 branes. Like that's the way we engineer the SQCD. Then we know that S-duality acts by swapping D5 and NS5. Taking also into account the brane creation effect, one can dualize this setup into its dual, and then you can read off the theory from the branes to find the mirror dual theory. So that's a way to construct mirror dualities. But now I want to show you a different type of approach, because this will be the one that I will extend to the n equal to 2 case. And this is given by this purely quantum field theoretic approach of the dualization algorithm. So the idea is that we take a theory, and first of all, we want to break it into basic QFT blocks. And this is done by engaging all the gauge symmetries. And you can intuitively think that each block corresponds to a single 5 brane. So for example, we have a block corresponding to a D5 brane with ND3 stretching on the left and on the right. And this is given at the QFT level as a flavor block coming together with this identity operator. This identity operator, you can think that as the effect of identifying the cartans of two UN symmetries. So at the level of the S3 partition function, this is just a collection of delta functions. You can think about it in this way. And also we have a second block corresponding to an NS5 brane with MD3 on the left and MD3 on the right. And this corresponds to an hypermultiplet in the bifundamental of UN times UM with some background parameter, Fi parameter, given by this Y in red. So if we use this prescription, for example, in the SQCD, as I said, first of all, we engage the UN symmetry, and then we cut it into blocks. And we recognize that on the two sides, there are these two trivial bifundamentals. And by trivial, I mean that those are just zero hypermultiplets. So there's not really any matter in this block. But there's this background Fi parameter for this UN symmetry, and similar story on the right. Then we see that in the middle, we have the F flavors that we split as F single flavor block. And all of them come together with their corresponding identity operators. So that's how we cut the SQCD into blocks. Now, what we want to do is that we want to use a set of basic mirror dualities to dualize each block, and then glue together all the result of this dualization. And we dualize them using this genuine infrared duality given in this picture, where on the left-hand side, we have this, I would say, very complicated theory given by two TSUN that are represented by these two dashed lines. And we glue them together, meaning that we take a SUN global symmetry coming from both, and we identify and gauge the diagonal subgroup. And then we also add this extra joint A, and we couple it to the moment maps of the two TSUN. And this is encoded in the W gluing. And then we add also this flavor, and also this flavor is coupled cubically to the adjoint field. So that's the theory on the left-hand side. And I claim that it can be proven, iterating cyber-like dualities, that this theory on the left is dual in the IR to this theory on the right, given by this set of bifundamentals. And we want to interpret this duality as, again, intuitively, as the S generator acting on a D5 brane, dualizing it into an NS5 brane. So the S generator is represented by the two TSUN theories. The D5 is the n equal to 4 flavor block. And then on the right, we have the bifundamental. And so it's important.
I have a question.
What?
Are you familiar with the duality operations that an India Day is doing?
Sorry, what? The duality operation?
That the work of an India Day.
Oh, sorry, I think I'm missing the name of this duality.
The name, the person is called an India Day.
No, I don't think I know this.
Yeah, I wanted to see if there is any connection between the work you're doing and what he's doing. Anyhow, if you're not familiar. Yeah.
No, I'm not familiar with that. I'm sorry.
Okay, thank you.
So far, I don't see a direct connection. But so here, what you're doing on the left, just to clarify, it's a quiver. If I write this as a standard quiver, then it goes from 1 up to n, down back to 1.
Yes.
And you one node on the n.
Yes.
The Coulomb branch is h to n squared, and then the Higgs branch is trivial.
Yeah.
Yeah. Okay.
That's the theory on the left. Yeah. You
okay, very nice. So this is a well-known. Yeah, good.
Okay, so I will say that we are thinking of the TSUN theory as the S generator of S duality. So indeed, we expect it to satisfy some set of QFT relations that corresponds to all the algebraic relations satisfied by the S generator. So for example, let me take the most trivial one. So we expect that S times its inverse is equal to the identity. And this is encoded in this duality here, where we are gluing together to TSUN without matter. So this is just the operation of S times S to the minus 1. And when we do that, we obtain an identity operator. And I think I can give you an intuitive way to see this relation by telling that if you set n equal to 1, the theory on the left becomes just a free vector multiplet with some background, with some fi parameter given by x minus y. And it is known that this theory, at the level of the S3 partition function, behaves as some delta function setting the phi parameter to 0. So you can think of this more generic identity as some non-abelian generalization of this property. Good. So to recap, the idea is that, again, we take a theory, engage the gauge symmetries, cut it into basic QFT blocks, dualize each of these blocks, and then glue back the results. And also, let me add that in the end, one usually finds some VEV in the resulting theory, so you should study them and follow their G flow to get the resulting theory. And even if I showed you this, let's say, more graphical way to see this algorithmic strategy, I want to tell you that actually each of these steps consists in some rigorous mathematical manipulation of the partition function. So because of this rigorous nature, we end up with some exact identity between the partition function of the original theory and its mirror dual. So for example, we know the exact map between the parameters of the two theories. And that's very useful when we want, for example, say to map operators or turn on some deformation, gauge some symmetry. It's very useful to know the map between parameters in order to do that. But also we know all the exact background couplings that should be added in the identity between partition functions. And these we found to be very interesting because they seem to be tightly connected to mixed anomalies and these kind of things. And we are currently studying this point of view. So that's all I wanted to tell you about mirror dualities with 8 supercharges. So now if there's any more questions, this would be a good time before I move on. Okay, it seems that everything is clear, good. So now before I move on to the 4 supercharges case, I want to introduce a theory that, as I already said, will be used as a basic block to construct 3D n equal to 2 dualities. And this is the so-called FMUN theory that I will always, well, always really refer to as the generalized bifundamental theory. And I think you will see the reason very clearly in a couple of minutes. So this theory is the 3D n equal to 2 superconformal field theory living at the infrared fixed point of this UV Lagrangian description. And the theory is given by n-1 unitary gauge nodes of ranks from 1 to n-1 that are connected by these bifundamentals so that the last one is rotated by this UN favor symmetry. And we also couple cubically all the bifundamentals to these extra joints. Then we also add this saw-like structure to the theory. And this is characterized by those U1Y symmetries rotating these spirals. And we want to couple cubically bifundamentals and diagonal legs in this way, so that for each triangle we have a cubic interaction. And then to conclude, we break all the topological symmetries by introducing a monopole superpotential for each unitary gauge node. So that's the result.
Why is it called the FM?
FM, I think it's just a name. So F stands for flip because there's some extra singlet, and M, I'm not really sure why is it called M. It was a name introduced in this work.
I see.
It's monopole because of the monopole superpotential.
Thank you. Okay, thank you.
F is what again?
F is the flipping field.
Free field?
It's a thing that flips.
Flipped monopole. I see. Okay.
It's the flip of the meson matrix.
I see. Okay. Thank you.
Okay, thank you, Matteo. So the resulting theory will have some symmetry so that we have this UN flavor symmetry rotating the last bifundamental and this diagonal left. And also I claim that in the IR, the NU1Y symmetries are actually enhanced to a UNY non-abelian global symmetry. And effectively, actually, we have UNX times UNY moda U1, because we can reabsorb this U1 by gauge transformations in the Lagrangian theory. And then we also have these two extra U1 symmetries that are axial-like symmetries compatible with the superpotential that we turned on. And probably the most important property of this theory is that it is self-dual under a mirror-like duality that acts by swapping the manifest, so the UNX symmetry, with the emergent one, so the UNY. And because of this property, we find convenient to depict the theory as a single block given by these two wavy lines connecting two UN symmetries, and we are not declaring which of the two is actually the emergent or the manifest symmetry, because we are always free to make this choice by means of this self-duality. Some important information is the spectrum of gauge invariant operators of this theory. So there are mainly 4 operators that I will use in this talk. 2 of them are adjoint operators. So we have this AX, which is in the adjoint of the manifest UNX symmetry and is given just by this singlet. And then we also have this AY, which is in the adjoint representation of the emergent UNY symmetry. And this is obtained by collecting many operators. So we take the mesons that we can construct that are charged under 2 U1Y symmetries. So for example, we take this operator, but also this longer meson, also this one, and all the other similar operators. We collect all of them and we obtain some matrix transforming in the adjoint of the emergent symmetry. And something very interesting is that these 2 operators, AX and AY, have the same R charge. And that's consistent with the fact that if I apply the self-mirror-like duality, we swap the 2 symmetries. So we are also swapping these 2 operators. Then we have also this pair of bifundamentals, which gives the name to the theory, generalized bifundamental. And these, again, are obtained by collecting many contributions. So we take mesons that are charged under 1 UY symmetry and the UNX symmetry. And so, for example, we have this meson, this other one, this singlet, and so on. And if we collect them, we can construct these pi and pi tilde operators, one in the n and bar, and the other in the n bar n of UNX times UNY. And then to conclude, let me also mention that we can construct many singlets. And by singlets, I mean singlets under the non-abelian global symmetries that we can collect into some metrics that I will call generically B and M. So this is the spectrum of gauge invariant operators. And the last bit of information that I want to tell you about this theory regards the deformation that we can turn on. So there are 2 types of deformations in which I will be interested in. One is given by superpotential deformation and the other by real masses. So let's focus on the first one. I can, for example, turn on some linear superpotential by introducing one of the B and M singlets in the superpotential. So these do not break the UNX and UNY symmetries, but just break the U1 delta and U1 T axial-like symmetries. And for example, if we turn on this B11, it can be proven that the generalized bifundamental behaves as an identity operator. And the way we interpret this relation is that when we turn on this superpotential, the pi and pi tilde bifundamentals acquire some VEV, so that everywhere on the moduli space, the UNX times UNY symmetries are broken down to the diagonal UN subgroup. And that's encoded in this identity operator. But also we can turn on, for example, B12, so a different singlet, and this has a completely different effect. what happens is that the generalized bifundamental now becomes a standard one that is also coupled to these two extra adjoint chirals. So we will have some cubic interactions, say QQ tilde A1 and QQ tilde A2. Then we can also consider superpotential deformation that have the effect of breaking the UNX and UNY symmetries. And for example, we can give a nilpotent mass to one of the two adjoint operators. Say that we do this to the AX operator. The effect I claim is to give this set of n hypermultiplets together with this cross that represents some set of singlets that is coupled to these hypermultiplets. So that's the story for superpotential deformation. Now, as I said, we can also turn on real masses. And for example, if we turn on a real mass for the U1 delta symmetry, what we are doing, so we give mass to all the fields that are charged under U1 delta, we obtain that the generalized bifundamental becomes a TSUN. And I think this can be seen clearly from the UV description, because the only fields that are charged under the U1 delta symmetry are those in this SO-like structure. So when we give a real mass to them, we remove them, and we also restore all the topological symmetries. So we are left with this tail of increasing ranks, which is precisely the TSUN, modulo maybe some singlet that is present in the theory. Okay, so that's everything that I wanted to tell you about this generalized bifundamental theory. Now I'm fully ready to talk about 3D n equal to 2 mirror dualities. And in particular, I want to show you our proposal for the 3D n equal to 2 mirror dual of the UN adjoint SQCD. So here we have the duality that we found. That seems very complicated, but I will now explain to you how this goes. So on the left, we have the n equal to 2 UN adjoint SQCD, which is given by a UN gauge group. We have this extra joint chiral and F fundamental and anti-fundamentals. But now there's no n equal to 4 supersymmetry forcing a cubic interaction between the flavors and the adjoint. So the real flavor symmetry of this theory is truly a UF times UF, rotating independently fundamentals and anti-fundamentals. So we have double the flavor symmetries. And we find convenient to actually reparameterize the theory in this second alternative way, where we have paired fundamentals and anti-fundamentals into a F set of single flavors. So we have these F flavors, and each of them is characterized by a U1x vector-like symmetry and a U1b axial-like symmetry. And by this 1 minus B1, I just mean that we assign a trialar charge of 1 to all the chirals, but along the RG flow, this trialar charge can mix with the axial-like symmetries. And by 1 minus B1, I mean that we are mixing with the U1, B1 symmetry, and B1 is the mixing coefficient. So then also we have the chiral, which can be rotated independently by some U1 called the T symmetry. And also we have a topological symmetry that I parameterize with this Y1 minus Y2. And I claim that this theory is dual to this other theory on the right, which is given by F minus 1 UN gauge nodes linked together by F minus 2 generalized bifundamentals. And we also introduce this W gluing superpotential, which couples all these explicit adjoint chirals to the adjoint operator living inside the generalized bifundamental. So that's encoded in this W gluing term. Then on the two sides of the quiver, we have these flavors that comes also together with these two crosses. And the crosses is just a graphical way to tell that we have a set of n singlets that flips the meson built from the flavor, dressed with powers of this adjoint field from power 0 to power n minus 1. So we are flipping all of them. And same story for the other flavor. So that's the duality. And now I want to map the symmetries between these two theories. So in the SQCD, we have a UF times UF flavor symmetry that rotates fundamental and anti-fundamentals. And I can mod out a U1 gauge transformation. Then I also have this U1 T symmetry rotating independently the adjoint and the U1 topological symmetry. And in the mirror theory, this global symmetry is not manifest, but in the UV is visible only the Cartan subgroup. So there will be some enhancement in the IR that gives this complete non-abelian global symmetry. And this pattern of enhancement, I think it's clearer if we look at the operator map. So again, similarly to the n equal to 4 case, we have mainly two operators to map that are the meson and the monopoles. So let's start from the mesons. I will split this operator into two types of contribution. We have these, what I call diagonal components that are given in this parameterization by those mesons that I built by taking a fundamental and anti-fundamental living inside the same flavor block. And notice that the obtained operator is not charged under the U1 vector-like symmetry, but is only charged under the U1 axial-like symmetry. And we map these F operators to singlets that we have in the mirror theory. So for example, if I do this procedure for the 8th flavor, I will map it to a singlet inside the BNM matrix of the 8th generalized bifundamental. But if I take A equal to 1 or A equal to F, it's slightly different because instead I will pick one of the singlets living inside this tower of n singlets. On the left for A equal to 1 and on the right for A equal to F. Then we also want to map these off-diagonal components that are obtained by taking a fundamental and anti-fundamentals living in two different flavors. So for example, we can do this x1, xa, and of course we have another meson given by xa, x1. And these two will be charged under both the vector-like symmetries and the axial-like symmetries. And we map them to a set of monopoles that we can construct in the mirror theory, and say that we are doing, like in this example, we are considering the x1, xa meson. We will take the monopole that has a positive charge under the first, second, up to the A-1 topological symmetry. And then the other operator will be given by the same monopole, but with negative charge. So that's how we map these mesons. Then we have the monopoles, and here we have a very similar story. So we have two monopoles to map, and we map them to two mesons that we construct by taking a flavor, multiplying by this string of bifundamentals. So we take the pi or pi tilde operator living in the generalized bifundamental, and then again the other flavor. There are two such operators with opposite charge under the U1 flavor symmetry in the mirror theory, because again, we have two, originally we have two U1 symmetries, but we can mod out a U1 gauge transformation. So effectively we have just one. And these two mesons are mapped to the two oppositely charged monopoles. And I want to underline that exactly as in the n equal to 4 case, in this duality, we are mapping vector-like symmetries into topological symmetries. But now we also have, in this n equal to 2 case, axial symmetries. And in this duality, we observe that axial symmetries are mapped again in axial symmetries. And this, I think, is an interesting feature of this duality. So now, before I move on to describing how we can derive this relation, I just want to show you a couple of consistency checks that we performed, probably the most basic ones. The first one is given by masses to a flavor. So we take the SQCD and we give a complex mass to one flavor. So we reduce the parameter f to f minus 1. So we expect that the effect in the mirror theory is to shorten the number of generalized bifundamentals, or shorten the number of gauge nodes, because there is where enters the F parameter. And we found this to be true because thanks to the operator map, we know that this complex mass deformation maps to a linear superpotential for a B11 singlet living inside, say, the first generalized bifundamental. And as I said before, if I just go back some slides, if I turn on the B11, the generalized bifundamental becomes an identity operator. So effectively what happens is that we are getting rid of one generalized bifundamental and we are identifying these two UN gauge symmetries. So the net effect is to shorten this sequence of gauge nodes and generalized bifundamental. So this is consistent. And the less trivial check is instead given by an n equal to 4 limit. And what I mean is that we can turn on the cubic superpotential coupling flavors and adjoint. So we obtain the n equal to 4 UN SQCD. And indeed, we expect that the mirror dual becomes the known mirror dual for the n equal to 4 SQCD. And this again is true. And what we find is that if we map this deformation in the mirror theory, we have two effects going on. The first one is that we are turning on linearly all the B12 singlets that, again, if I go back to the same slide, if I turn on this B12 deformation, the effect is to make the generalized bifundamental into a standard one. So what we are doing is that we are ironing all the generalized bifundamental down to standard ones. And then there's a second effect, which is that we are turning on a VEV for the meson obtained from the vertical flavors dressed n-2 times with the adjoint. And if we study these VEVs, we observe that, first of all, the effect is to X the first and last UN gauge symmetry down to U1, but then this also triggers a second VEV for the second gauge node, which exits from UN down to U2, and then again, this triggers a third VEV that takes the third node down to U3 and so on. So these VEVs propagates towards the center of the quiver, and given that we have enough gauge nodes, so given that 2F is greater or equal to N, which is the good condition for the SQCD, we find that we reconstruct these two tails of increasing ranks on the left and on the right, and then the flavor will just sit on the sides of this plateau. And that's exactly the known mirror theory of the n equal to 4 SQCD. So also this check is passed. And as a last information about deformations, I want to tell you that we also know how to perform real masses. And that's very interesting because using real masses, we can now deform the theory to some SQCD with non-zero Chern-Simons level or even with chiral matter content. So here the story goes as follows. Suppose that you start with a SQCD, UN SQCD with 0 Chern-Simons and say 5 flavors. So its mirror will have 4 gauge nodes linked by 3 generalized bifundamentals. Now I perform a real mass for a flavor. So the effect is to lower the number of flavors from 5 to 4 and also increases the Chern-Simons level by 1 unit. And we know how to map this deformation in the mirror theory. And the effect is to take a generalized bifundamental and making it into a TSUN theory with some background Chern-Simons levels. So you can see that the effect in the mirror theory is to replace a generalized bifundamental, like in this picture, with a TSUN and also introduces these Chern-Simons levels. And you can generalize this story to find more generic theory with higher Chern-Simons level. But we can also play a different game. So we can give a real mass to only one fundamental. So we just lower the number of fundamentals and increase the Chern-Simons level by 1/2. So we'll obtain a theory with chiral matter content, and we know the effect of this deformation. And even though I haven't really explained what this theory is, let me just anticipate it by saying that this deformation makes the generalized bifundamental into what I call a generalized chiral. That comes also with these background FIs, background Chern-Simon, sorry. So if we use this in the mirror, you see that a bifundamental, generalized bifundamental link is now replaced with this generalized chiral and also turns on these half integer Chern-Simons levels. So what's this generalized chiral theory? The theory is very similar to the FMUN and it's called FC, where C stands for chiral, I suppose, here. And the idea is that we have integrated out from the theory just half of the so-like structure in the FM. So now we have a theory whose spectrum is given by two adjoint operators, one for the UNX and one for the emergent UNY symmetry. But then instead of having pi and pi tilde, we have just, let's say, pi, so one bifundamental. So that's why we call this theory a generalized chiral instead of, say, a generalized hyper. And again, we find convenient to depict this theory as a single block because also this theory enjoys a self-mirror-like duality, where we swap the emergent and manifest symmetry and change the direction of this so-like structure from being from the right to the left to being from the left to the right. Okay, so that's the story about deformations. Now I want to tell you how we can derive these type of dualities. So the idea is, so maybe before I go on, is there any question? It would be a good moment. Okay, now it seems that everything is clear. Nice. So now the idea to find these 3D n equal to 2 mirror dualities is that we can again use the dualization algorithm, but we need a new basic n equal to 2 mirror-like duality. So again, the story is to take a theory, engage the gauge symmetries, but then we will cut the theory into n equal to 2 blocks. So we will have n equal to 2 flavors, and these n equal to 2 generalized bifundamentals that we dualize using this infrared duality. So on the left-hand side, we have again two TSUN glued together. And then in the middle, we have this flavor, which is not coupled to the adjoint. So that's why we are interpreting this as an n equal to 2 flavor, because that's an n equal to 2 theory. And we prove that by iterating cyber-like dualities, in this case, Aroni duality, we can show that this theory is dual to the generalized bifundamental. And we want to interpret this duality as the S generator given by the 2TSUN acting on an n equal to 2 flavor, giving an n equal to 2 bifundamental. So you can think about this, and I will come back to this point, as the S dualization of a D5 brane into an NS5 brane, but inside a brane setup, which is 4 supercharges preserving instead of 8 supercharges preserving. And indeed, you may wonder whether this basic mirror duality reduces to the n equal to 4 mirror duality. And that's true. If I add the cubic superpotential that couples the flavor to the adjoint, we can map this deformation on the right-hand side, and the effect is to make the generalized bifundamental into a standard one. So we recover the n equal to 4 basic mirror duality. So now let me show you very schematically how this procedure of dualization goes. So the idea is that we start from the SQCD, and first of all, we reparameterize it in this way. So we split the flavors into pairs of fundamental and anti-fundamentals. Then we engage the UN gauge symmetry, and cut the theory into blocks. So we recognize, exactly as in the n equal to 4 case, these two trivial bifundamentals. And again, those are trivial because there's no matter here. This is just some background Fi. And then on the center, I recognize F flavor blocks that now are n equal to 2 flavor blocks. So each of them is rotated by some U1 X axial-like symmetry and a U1B, sorry, a U1 X vector-like symmetry and a U1B axial-like symmetry. Now I use the duality that I've shown you before to dualize each block so that each flavor becomes a generalized bifundamental. So we end up with this string of F generalized bifundamental besides these two TSUN. So this comes from the dualization of just the flavor blocks. And then on these two sides, we have the result of the dualization of the trivial bifundamentals. And this gives this deformed TSUN. And by this asymmetric picture, I mean that we take a TSUN theory and we perform a nilpotent mass for a moment map so that I will break the SUN symmetry down to a U1. So that's encoded in this picture. And again, I have another similar structure on the right. Now I use the fact that two consequent TSUN glued together behaves as an identity. But now we have a deformed asymmetric gluing of two TSUN. So instead of identifying this gauge symmetry with some other UN symmetry, the effect of this wall is to break this symmetry down to a U1. Effectively, what we are doing is that we are giving a nilpotent mass for the adjoint operator inside the first generalized bifundamental, and similar for the adjoint operator in the last bifundamental. And I have to go back again to the same slide to remind you that if I perform this deformation in the generalized bifundamental, so if I perform this nilpotent mass, I will end up with these n hypermultiplets coupled to these singlets. So if I use this information here, I find that the first and last bifundamentals becomes the flavors on the sides of the quiver, and then we are left with the remaining F-2 generalized bifundamentals linking the F-1 UN gauge nodes. And that's precisely what I claim is the mirror theory. And I want to tell you also that since each step corresponds to a rigorous manipulation of the partition function, we know how to map the parameters of the original theory at each step. So in this second theory, in this third one, and in the final frame. So we know exactly how the parameters are mapped. And thanks to that, it's easier to see how the operator map goes. So that's the crucial property of this strategy. So now I want to tell you something about our interpretation of this whole story from the point of view of brane systems. So it is known that we can engineer the n equal to 2 UN adjoint SQCD from a brane setup preserving 4 supercharges. So similarly, as in the n equal to 4 case, we take NS5 to NS5 branes, then we add these n d3s, and the flavors are given by these d5 prime. So, and d5 prime are just rotated d5 branes. So that if I take a d3 brane stretching from an NS5 to a d5 prime, instead of being locked in position, as in the n equal to 4 case, now it is free to move in 2 directions. And because of these extra, let's say, degrees of freedom, we obtain a theory with more degrees of freedom, which is the n equal to 2 adjoint SQCD, which has more symmetries and less constraint because it has less superpotential terms. So we know how to perform S duality on this setup, and the result is given by this one. So we have swapped NS5 with D5, and D5 prime with an S5 prime branes. So just rotated an S5 branes. And then we can also run the algorithm and find this dual theory. And I think there is a nice way to interpret this relation, which is that the F and S5 prime branes gives the F-1 UN gauge nodes, given by the D3 stretching. The 2D5 on the two sides gives these flavors on the first and last gauge node. But now notice that instead of having naive standard bifundamentals, it seems that it's more correct, or at least more useful, to use generalized bifundamentals that carry an extra U1 symmetry, and because of that, we can match the extra symmetries that we have in the original theory of this flavor doubling, because we have no cubic superpotential. So now we can take this result and make it into a prescription. So say that if I give you a more complicated setup, I will use generalized bifundamental instead of standard ones. So for example, I can construct a theory with two gauge nodes given by 3 and S5 branes with some F1 and F2 flavors on the two nodes. And now I will put a generalized bifundamental. Then I can S-dualize the setup to obtain this other one. And I can also run the algorithm to find this dual theory. And if you use the same prescription that I told you to read the theory from this setup, you will obtain the same QFT. So a theory with generalized bifundamentals and flavors with flippers and so on. And that's probably the most important punchline of what I wanted to tell you. So now let me go to the conclusions. So a very brief recap of what I say is that we have found an exact mirror dual for the 3D n equal to 2 adjoint UN SQCD. And while doing so, we generalized the strategy of the dualization algorithm. So now we are able to dualize and find the mirror dual of more complicated theories, like theories with more nodes. But also we have proved that 3D n equal to 2 mirror duality can be seen as a consequence of more fundamental cyber-like duality. Also, we found a way to deform these theories to find more generic n equal to 2 theories, like theories with chiral matter or Chern-Simons level. And we also give an interpretation of this story from the point of view of brane setups preserving 4 supercharges. Now, there is also something that I never told you during the talk that lives in 4 dimensions. So I now tell you that you can take this whole story that I just told you, and there is some generalization to 4D n equal to 1 theories. So we, and this generalization goes as follows. So instead of having then the UN SQCD, we will have the USP2N for the n equal to 1 SQCD, for which we found a mirror-like dual, which is a 4D n equal to 1 theory, with a similar pattern of mapping of operators and enhancement of symmetries. And if you perform a dimensional reduction limit of this duality, you will end up with the mirror duality for the SQCD. So what are possible future perspectives? First of all, I think there is an obvious one, which is try to study more generic brane setups. So for example, a requirement for the setup that I showed you before is that we must have a constant number of D3 branes, because we do not know at the moment what happens if you put, say, N D3 and M D3 in this other segment. So it will be interesting to find out what's happening there. But also we can, like, for example, insert PQ webs inside the setup, or even involve more type of branes. So again, you can notice that here I'm always using one type of an S5 and one type of D5 brane. Now I can ask what happens if I use both an S5 and an S5 prime, or D5 and D5 prime, or even the 4 together. And that again is something that it's not completely clear at the moment. But also, since there is this whole uplifted story in for d n equal to 1, I think it would be also interesting to understand if we can systematically construct the 3D mirror of for d n equal to 1 theories. And this would be also interesting. And that's basically all. Thank you for the attention.
All right, let's thank Riccardo.
Thank you.
Do we have questions? Moment. So, are there some self-dual cases, like in the last example you showed us?
In this quiver?
Yeah, if I pick like F, right, are there some self-dual cases?
Yeah, there are self-dual cases.
Is
So,
there anything nice about them? Or...
well, there could be something nice about them, sure. Well, for the SQCD, there is a self-dual frame when I take two flavors.
Sure, yeah, that's yeah.
But that's
An
known.
extension of this, yeah.
But also here, you see, I think if I put like
1 and 2,
like 1 and 2, I will end up with a self-dual theory. So that's interesting.
Cool. Very nice.
Sorry, can I ask about this precise example? I don't follow the two flavor nodes in the middle gauge node in the quiver.
Okay. In this theory that I'm showing now.
How do we read this setup? Yeah.
Okay, sorry, I think you lagged a bit, so I haven't heard the question.
I didn't follow. How do you read in this example the quiver from the brane setup? In particular, I'm a bit confused by the two flavor nodes in the middle node in the quiver.
Okay, on the right-hand side.
Yeah.
So the idea is that we have this central gauge node given by this 2ns5 prime, okay? And this d5 is a flavor for the central node, but that's an n equal to 2 flavor. So I write this in this way. You can think that it's exactly as in the n equal to 4 case. You would put a fundamental and anti-fundamental, but now I'm drawing them split because I have an extra U1 symmetry rotating them. So that's how I read this central flavor.
Yeah, thank you.
Any more questions for Riccardo? Well, then I'd say it's time to go off record. We can thank him again.
Thank you.
And we can, of course, stick around.